All right, guys. So yesterday I posted the homework solution for homework number 8. So you will find it in the modules of Friday and also homework 7 and homework 6. So almost all of the homeworks that is not due on next few days are. And I think we will have a help session today at 1 p.m. So if you have any questions, come with your questions and we can solve them together or give you some tips how to solve the homework questions. And also, if you have any questions related to your studying for quiz, so that's totally fine if you want to come and ask your questions. So, does anybody have any questions so far on the content that we take or any issues, concerns? Okay, so yesterday we started the concept of conservation of energy and showed that the equation of the that relates the work and energy is the same as the one that has the conservative forces. So based on yesterday lecture, so we have T1, which is the kinetic energy. Like let's assume that we have a body here and we'll come to this location. So this is one, this position one, and this is position two. Here start by velocity v1, and here has a velocity v2. So our our equation is t1 plus the sum of the work, all the work, not only the conservative work, from 1 to 2 will be equal to T2, the kinetic energy at 2. And this is equal half mv1 square plus the sum of work from 1 to 2 will be equal half mv2 square. So if you choose to use this, you will have to include in the work done by any force or weight or spring. So you know that the force will be the integration of F cosine theta ds, and the weight is equal to W delta Y, and keep attention that the work depends on how the weight is moving. So if your weight is here and it's going up, so it's a negative. So this is a negative work. And if the weight will come down, so it's a positive work, because this body it doesn't have any work to be done to go down there, so he can't do it in its own. But here you have to exert some work on this body to get it up there, so it takes negative sign. And the spring is always, in terms of work, is always negative half k delta s square, and this is equal to S2 square minus S1 square. So the final elongation minus the initial extension. So this is how you calculate the work in terms of here. But if you choose, so this is our versed equation. Also, you might want to use another equation which will give you the same answer, which is the T1 plus V1 plus the work from 1 to 2 only by non-conservative forces will be equal to T2 plus V2. And this is equal to, T1 is equal to half mv1 square, and V1 is so V is the potential energy of weight and also the spring, elastic spring. And this is equal to mgh 1 plus half k s1 square. So this is v1. So this 2 is related to v1 plus the sum of u from 1 to 2 done by the non-conservative forces will be equal to half mv2 square plus, actually, yeah, plus mg h2 plus half k s2 square, and this is related to v2. So this is how does the equation look like, and pose this equation and this equation, equation 1 and equation 2 should give you the same answer. But here in this equation, you have like, if your body, like let's say, here's your body and here's your body, you will have to assume a datum to measure from. So here's a datum, and the body start from here, so the H1 is 0. But if your body is here above the datum, so it has a potential energy, a positive H, and it's below the datum, it has negative H. You can assume the datum at any location. You can assume it up there, you can assume it here, whatever you want. All of them will give you the same answer. Just like pick a datum, and if your body is above the datum, so it will have a positive edge. If it's below the datum, it will have negative edge. And also for the K of the spring, so for the K of the spring, the potential energy in the spring is always positive, as we discussed last time. So if you have a spring like this, and you stretched the spring S1 like this, so S1 is measured from the unstretched length, unstretched length. So this is O and this is 1. So S1 is from the unstretched length to the position 1, and if it came to position 2 here, so this is S2, and also it's positive. So let's see an example how both equation 1 and equation 2 can give us the same answer. So let's start with this spring example, and actually we solved this problem, if you remember, in the Newtonian kinetics using the force and acceleration. But let's now solve this problem using the conservation of energy. So okay, so here it says that this is the where the spring, so the spring was unstretched at point A, and here's a collar that moves on a rod, and A moves down to C, cutting distance Y, and Y is equal to 1 meter. And so it's fits loosely on the vertical shaft, means that there is no friction. If the spring is unstretched when the collar is in position A, so this is the unstretched length, 0.75 meter, determine the speed at which the collar is moving when Y is equal to 1 meter. So it needs the speed at C if it's released from rest at A. So V at A is 0. So this is for A. So there's two requirements, A and B. The first one assumes that A starts from rest, and the second assumed that A starts with upward velocity of 2 meter per second. So you will have to work on both. Like the first part you will have to do with the V0, and the second one you will have to work with the V is going upward 2 meter per second. If you are going to solve this problem using the Newtonian kinetics, but this is what we are not going to do this here, but I'm just like showing you an example. You will have to draw a free body diagram for the collar and put all the forces. So you will have F spring like this, and you will have weight go down like this. And actually, when the spring pulls this collar, there will be a normal force from the rod to the collar, so it will be something like that, which restrains this collar from going this way. So this is the normal force direction. All right, and then the second thing is this is the free body diagram, and this is the kinetic diagram. And second is that you will put here like the x-axis, and here's the y-axis, and assume that the motion, all the motion as we can see from here, it's in the y direction. So this is m-a-y, and then you solve this problem using Newtonian kinetics. But what is required in this problem, and I think it's better because the velocity is given at the initial location and the final location. So when the velocity is given, knowing the mass of the body, so you can get the kinetic energy at the starting position and the kinetic energy at the final position. So that's will help us. So let's first use T1 plus the sum of all the work from 1 to 2 will be equal to T2. And we will start by the requirement number 1, which is VA is equal to 0, assuming that the body starts from rest. Okay, so what is the forces that exerting work on this body? So right now we put 3 of them here. So does anybody know, is that all of these forces exerting work, or just like few of them?
It should just be the force of the spring and the weight, or a component of the force of the spring.
Exactly, yeah. So just like the weight and the spring. But here in this problem, and actually it's concerning to me, from my perspective, I think that from my perspective, that one component of the spring is the one that exerting work. So if you analyze this spring, you will have Fs cosine theta and Fs, like if this is theta, and Fs sine theta. And I can see that Fs is the one that exerting work, but based on the conservation of energy, as we talked last time, like the spring, it doesn't depend on the path, like just like we are thinking about the whole system, the energy in the whole system. So when we are talking about the spring, we will be considering that all the spring is exerting the energy. So let's say show you, like if you have the Kepler textbook, he will tell you that this problem can also solve it by using the equation of motion, which is the drawing the free body diagram. Note that for both of these methods, the variation in the magnitude and direction of the spring force must be taken into account. So you will have in both of these methods, you will have to take into account that the Fs is changing, like if here, when the spring is at this location, actually has different theta. So the magnitude, like you will have different components. And if it's at this location, you will have different theta. And at this location, you will have different, so theta is changing so the F spring is keep it changing over the motion. But what Hebler did here, he said, however, the above solution is clearly advantageous since the calculation depends only on the data calculated at the initial and final points. So here we will just like considering that the total force in the spring doing energy, not just one component, because we will be thinking about the whole system, not the only force exerted on this body. So here we will be considering the whole energy in the whole system and stored the energy in the spring and all the spring. So we will be considering, because this equation is not for one body, it's for the whole system. So we will be considering the energy in the whole system. So the only forces that will be exerting or doing energy or having energy or work, it will be the W and also the F spring. So let's remove these components. Okay. So let's see. First, at position 1 here, VA, so here it will be half M VA square plus the U done by the weight plus the U done by the spring. So this is the sum of U from 1 to 2 will be equal to half MV at C square. And what is required in this problem is the VC. So let's construct our problem. So we'll have half multiplied by the mass, which is 2 kilogram, multiplied by VA square, which is 0. So because the first one, we will assume that VA is equal to 0. Let's see the work done by the weight. So what is the work done by the weight? So we have the weight start from here and go down here. So we have the weight is going down and we have our position is down. So the weight and the position are in the same direction. So it will be the weight of the color, which is the mg. So W weight is mg multiplied by delta y, and it's a positive. So 2 multiplied by 9.81 multiplied by delta y. So delta y is equal to 1, which is given. And the work is positive because the weight is going down, it's not going up, and also our position is going down. So both are in the same direction. But if in your problem, your body is going up and the weight is going down, so this is a negative work. All right, so the next is the work done by the spring. So we know that the work done by spring is always negative, so it will be negative half multiplied by K, and the K of the spring is given 3 Newton meter, multiplied by the S2 square minus the S1 square, or multiplied by the delta Y square. Delta Y squared. And delta Y here, look, just like to not confuse you because we have another Y, so delta S, because when I say delta Y, you might think about this Y, but we need the delta Y in the spring. So let's get the delta Y in the spring. So delta S in the spring, or delta, whatever works for you. So delta will be the L minus L node. So L node of the spring is 0.75 meter. And the second position of the spring, when it came here, we know that y is equal to 1 meter. And we know, what else do we know? So 1 meter, yeah, so just these two. So you know the this is 1 meter, and this is 0.75. So you can get the L of the spring at position 2. So L at the spring of the position 2 will be equal to root 1 square plus 0.75 square, and this will give you 1.25 meter. So you know the final L and the initial L. So this will be equal to 1.25 minus 0.75. So this will give you 0.5 meter. So this is the delta happened from the spring. Like if this is, so this is part is the stretch in the spring. So we will put it here and it will be squared, and it's negative because we know that the work exerted by the spring, not the energy, the work is negative. So let's put 0.5 here. And all of these will be equal to half multiplied by m, which is 2 multiplied by vc squared. So we know everything in this equation. This part will be 0. You can calculate this part and this part, and then you can get vc. And when you calculate vc, it will be 4.39 meter per second. So this is using the concept of the relationship between work and energy. So let's try solving the same problem using the conservation of energy, using this equation. So using this equation, Let's clear this things. Okay. So to use this, we will have to construct a datum. So let's assume our datum is here. This is the datum. So we can measure the so we can measure the potential energy of the weight. So here we will have, so let's write the equation. Actually, it's a long equation. If we can copy it, no problem. So let's write it again. So it's half m1 v1 square plus mgh1 plus half k s1 square plus the work done by the non-conservative forces will be equal to half mv2 square plus mgh2 plus half k s2 square. So let's put the components and let's see what is equal to 0 here. So we know that v1 is equal to 0. So this part will be equal to 0. And also we know that our datum is here. So the h at A is equal to 0. So this will be 0. And also we know at A that the spring is unstretched. So this part will be also 0. And we don't have non-conservative forces because the only forces that we have is the F spring and the weight. So this is the only two that can have work, and both of them are conservative. So we don't have any initial force. So if you are given that there's some kind of force acting on this body and you are given an equation or a value, so this will be non-conservative force and you will have to include it in this term. But we don't have it. So this term will be equal to 0 as well. So all the left-hand side will be equal to 0. So let's see what we have. So 0 will be equal to half the m is 2 multiplied by v2, which is vc square, which is the required in this problem, plus, let's see, it's a plus or minus. So here point C is below the datum. So what is the sign of mgh2? Does anybody know? Is it positive or negative?
It would be negative, wouldn't it?
Exactly, because it's below the datum, it doesn't have an energy to go up the datum. But if it's above the datum, it will have a positive potential energy to go down. So if it's below the datum, it will be negative, and this will be mgh2 multiplied by 9.81 multiplied by h2. So h2 is equal to 1 meter. And actually, you can actually put positive here and put the negative in 1. So whatever works for you, but I just like put the negative down there and put the whole energy as an absolute value. So whatever, if you want to consider that this is -1, so you put -1 here, but you put positive here. So you can have positive and you have -1 here, whatever it feels systematic for you and more easier, you can go ahead and do it. So the next term is the spring energy. So what is the sign of this energy, like this term? Is it going to be positive or negative?
Negative.
Actually, it will be negative if we are dealing with this equation as a work. Like if we are considering the spring is doing work, so it will be negative. It will be always negative here. But if we are considering the spring as an energy and we put a term on the left side and a term on the right side, so always the spring has positive energy. Okay, so this will not be negative. This will be positive. So, and I will prove to you both of the solutions are the same. So here, it will be half multiplied by the K of the spring is 3, multiplied by the S2 S2 of the spring. So let's see what is the S2. So the S is measured from the non-stretched length. So if the spring is like this, and you stretch it like this, this is the S at position 2. So this is S2. So S2 we just got it. It's a 0.5 meter, and we will put it 0.5 square. So this is how is our equation look like. And if you want to like get the VC, so you can send this term here and this term on the other side. So it will be, this is a negative term. When it comes to the other side, it will be positive. So it will be 2 multiplied by 9.81. And the negative one will be positive 1 because we sent it to the left-hand side. And this is a positive term. If you send it to the other side, it will be negative half multiplied by 3 multiplied by 0.5 square. And all of these is equal to half multiplied by 2 multiplied by VC square. I need you to look on this equation and look on the equation from here, this one. It's the same one using the same concept. So here is the weight, and here is the first term, and here is the second term, and it has a negative sign because we send it back to the other term. So that's the difference between the mentality. If you feel that this is confusing you, you might stick with this one and solve all your problems using this concept. If you feel, because I think maybe you studied this in the high school or in physics, with the conservation of energy, and you got this equation and you are fine to use this equation in your solution, just like go ahead and use this equation. And finally, you will get that VC will be equal to 4.39 meter per second. The second part, it will be like applying the same approach, but you will change because it's asked it to do the same thing with VA is not 0. It's equal to 2 meter per second, and it's upward. So you will have to put the VA in this equation. So it will be half 2 multiplied by the velocity, and you will take care about the signs because so you will have to be consistent where you with your sign. But actually, the consistency with these signs, it only matter in when you are calculating the forces. But in terms of energy, whatever the velocity, if it's going up or going down, so you will have half mv square. So if the velocity is negative, so you will have negative 2 meter per second, and it will be square, so it will be 4. So whatever it's positive or negative, because we are talking about energy right now. So this is, you will do the same thing and you will put VA, except like rather than having half MVA square equal to 0, it will be half multiplied by the M multiplied by 2 square, and do the same approach. Does anybody have any question? Does anybody want me to like do some illustration on this equation because it is not clear or the sign is confusing or anything? Just
I just had a quick question. So when you used that equation, and the S2 on the right side, you used 0.5.
yeah.
But earlier in the equation, in the first equation, we had used 0.5 as the delta S.
Yeah, so because in this equation, the S1 is unstretched, like this spring is unstretched, so S1 is equal to 0.
Okay.
Yeah, so let me like double check here.
Oh, I see. Okay. No, that makes sense now. I think
If,
I think that just, yeah.
yeah, if your spring has an S1 is not equal to 0, like here's the unstretched length, and S1 has a value of 0.25, like this is S1, and then you make more stretch and make like 1.5. So here you will have S1 and S2, and you will have to include both of them. So you will have your S1 here in this equation, so this will not be 0, and S2 will be the amount measured from here, the
Right.
1.5. Not the one measured from here. Okay.
Right. No, thank you. That clarifies. I appreciate it.
Okay, that sounds good. And I think, yeah, so we might like use the same concept and solve this problem. Let's solve this problem very quick. Okay, so for this problem, it says that the gantry structure in the photo is used to test the response of an airplane during a crash. As shown in this figure, the plane having a mass of 8 kilogram and is hoisted back until theta is equal to 60 degrees. So at this position, theta is equal to 60 degrees. And theta is measured from the vertical, and then the pullback cable AC, so this is a pullback cable, is released, so it will be released from this position. When the plane is at rest, determine the speed of the plane. So we know here that theta is equal to 60 and the VA is equal to 0 because it's released at rest. Determine the speed of the plane just before it crashes into the ground at theta equal 50 degrees. So we know that this is theta equal 60 and this is theta equal 15 degree. Also, what is the maximum tension developed in the supporting cable during the motion? Neglected the size of the airplane and the effect of the lift caused by the motion, the lift caused by the wings during the motion. Okay, so let's draw a free body diagram to identify what the forces that we have on this body. So if we have this is our plane, and it's attached to a cable, and this cable should be perpendicular to the body of the airplane, and it has tension T, and we know that there is a weight is going down like this. And if we want to know some angles at B, so let's, actually this is a big angle, but anyway, let's assume, let's be realistic here, and this is a small angle like this, and here's our body, and here's the tension, and here's the weight, and this angle should be equal to this angle, which is 15 degree. So this is how the set of forces acting on this plane. So let's see how can we solve this problem using the concept of conservation of energy. So the concept of conservation of energy, we will have T1 plus V1, and V1 is the conservative the conservative energy plus the sum of the work done by the non-conservative forces will be equal to T2 plus V2. And this is equal to half mv1 square plus mgh plus half k s1 square plus the sum from 1 to 2, and let's write non-conservative, and this is equal to half mv2 square plus mgh plus half ks2 square. So let's see what we have here. So VA, which is the V1, start from rest to this equal to 0, so this part will be 0. And let's say that we have the datum here. Actually, you can pick the datum here if you want. It will give you the same answer. So if we pick the datum above there, so we can get this, and this will be equal, so you have this angle is 60, and you know that tan 60 will be equal to x or h1 over, and actually it's given the cable length, it's 20, you have a rectangle, a triangle, And then you can get H1 will be equal 20, tan 60. And, oh, oh, sorry, this is not tan. This will be the cosine angle, sorry. So let's, like, not to confuse you, start from first. Okay, so let's make this a very clear triangle. So here, and here's our theta, and here's H1. And the cosine theta, H will be H1 will be equal to 20 cosine 60, because this is the line that we need to get. And the second one here, the theta will be 15, and this will be H2. So H2 will be equal to 20, not cosine 60, it will be cosine 15, which is the small angle, this one. So we got H1 and H2. And so what is the value of the work done by the energy at H1 at the energy at H2? Is it positive or negative for both? Does anybody know?
At H1, wouldn't it be 0, and at H2 would be negative because it's below the datum?
Actually, H1 is still below the datum here.
Oh, I see.
So if your datum is here, maybe I confused you. If the datum is here, so this one will be 0, and this one will be negative. But my datum is here, so the potential energy here is negative mgh1, and the potential energy here will be negative mgh2. So
That makes sense.
Sounds good. So here we will have the mass is 8 million gram. So 8 million gram will be 8,000 kilogram. And this will be multiplied by dg, which is 9.81. And you can put the negative in front of the h1, which will be negative 20 cosine 60. So for the spring, this problem doesn't have any spring. So how about the non-conservative forces? Do we have any non-conservative forces here? I mean, like non-conservative that exert work.
Would it be the cable?
Okay, let's think about it. So we have it here, and this one is cut, and this will be changed in the position. So if you think about the cable is always perpendicular to the motion. So like here, it moves in a circle. And we talked before that any forces that is perpendicular to the motion of the body, it doesn't exert work. So T, it doesn't exert any work on this body. Did you get it? Like it's something like you have a body is moving here, so the normal force that acting from the surface that the body moving on the body, because our motion in this way and the force is perpendicular to the direction of the motion, so it doesn't exert work. Similarly, if you have a body attached to a cable and your body is moving this way, so this force is perpendicular to the direction of the motion at any part, even if the body is here. So it will be perpendicular, like if it's vertical. So this body is moving this way and the tension is going this way. If you did a cross product between the F and the ds, cosine theta will be 90. So it will be 0. Is that clear?
Yeah.
Okay. So the tension in the cable is not exerting work because it's perpendicular to the body. But if we have a force, like if this helicopter or if this is plane have a motor and have a force like this, so this force exert energy because it's in the direction of the motion. But we don't have this in our problem. So this will give us, so this will be 0 as well. And let's continue writing our equation. Half, and the mass is 8,000 kilogram, and VC square, we don't know it. And we don't have a spring, so this part will be 0. Let's put MGH2. So MGH2, it will be 8,000 multiplied by 9.81 multiplied by H2, which will be negative 20 cosine 15, which is the value here. So now we construct our equation, and it will be easy to get the one unknown that we have here, which is the VC square. And from VC square, you will get VC, and this will be equal to 13.5 meter per second. So we got the velocity, and let's see how to use this velocity to get the tension, the maximum tension developed in the cable. Okay, so to get the maximum tension, we will have to go back to the Newtonian kinetics. So now we know the velocity of this at theta equal 15 degree. So we have V tangent of this body, and you know that the sum of forces in the tangent direction is equal to MAN, and we know that the EN is equal to the V tangent square over rho. Right now we have the V tangent, which is equal to 13.5 square, and we have the rho, which is 20 meter. So you can get the acceleration in the normal direction. So let's see what forces we have in the normal direction. Okay, I will draw this body again. We have the tangent, we have the weight, and we know the angle, 15 degree, and this is the free body diagram, and you can do the same thing here to draw so the tangent is always in the direction of the motion. So here's the tangent direction and the normal to the center of the curvature. And we assume that this is the direction of MAN, and this is the direction of MA tangent. So let's start by summation of MAN. So the forces in the N direction, we have the T, the tension in the cable, and we have negative W cosine 15, the component of the weight in this direction, and this will be equal to the mass, which is 8,000 multiplied by 13.5 square over 20. So actually you have the weight. So let's write the weight direct. So the weight is equal to, so here's the tangent minus the weight, which is 8,000 multiplied by 9.81 multiplied by cosine 15. So this will give you that the T, the tension in the cable, is equal to 149 Newton. So what we did here, it asks us for the force in the cable. And to know the force in the cable, you will construct a free body diagram. And when you start your Newtonian kinetics, you will find that the V tangent is missing, which is needed to calculate the normal acceleration. And to get the V tangent, you will use the concept of conservation of energy with half mv1 square on the left and half mv2 square on the right to get the V at the final position. And then when you get the V, you will go back to your Newtonian kinetics to get the tension in the cable. So this is how your workflow. Actually, you might start from the verst with the Newtonian kinetics because this is the verst, so to get the force. But when you realize that you don't have the V, you might think about other tools to get the velocity of the body. And then you might think about the concept of work and energy and start to set up your equation to get the V2. Does anybody have any question on this problem? All right, so I'll just want to do one last thing. Actually, I'm not going to start the new chapter, which is a chapter 15 right now, but I'm going to do something else. So let's, guys, that we will have quiz 3 tomorrow. Friday. And it will be 10:15 to 11:15, and it's a 30-minute. You can do it in any 30-minute between this time interval, and you will be tested in the chapter 12.10, which is related to relative motion, and also chapter 13, which is related to force and acceleration. And I totally recommend, so that there will be, I think it's the exam, the quiz is 20 points. And this 20 points is divided into 10 points on your right answers and another 10 points on partial credit. So the partial credit, you will be asked on the last question of the quiz to upload your handwritten answers. So please make sure to, because you only have 1 hour, make sure to access the exam at the right time, give you like a 2 or 5 minute to copy your handwritten, and make sure that you have your free body diagram with all the forces on the body and everything, because I will be giving points on the right free body diagram. And it's okay if you did mistake in the free body diagram in 1 or 2 forces, you will actually will not lose the full credit on the free body diagram. You might lose 1 or 2 points, but actually make your free body diagram, like if you are given a problem like this at any position, and there's a certain force going down like this, and here's a like normal force, and this body's moving this way, there's a friction. Put all the forces and draw a kinetic diagram, assuming that this is X, this is Y, whatever it works for you, assuming the direction of the MAX, the MAY. Put everything on your paper so you can make sure to get the 10 points of the partial credit. So this is for the quiz, and just like a quick follow up on the relative motion. So sometimes I can give you the like, that sometimes if you have maybe a road like this, and there's 2 cars here, car A, car B, and car A has a velocity VA, and car B has a velocity VB in this direction. So I don't have to tell you, maybe in the exam, what is the velocity of VA. I might like say that this is VA and this is VB, and VA is more than VB. So you know that VA in the I direction, so sorry, in the J direction, so this is X, and this is y. So this is the I hat direction, and this is the j hat direction. So I might tell you that VA is more than VB. Please find the velocity of B with respect to A, not as a value, but as a direction. Is it going this way? Is it going this way? Is it going this way or this way? So you know that VA is more than VB. So the J's component of this velocity is more than the J component of this velocity. So if you put, for example, like VA here, and you will have, for example, VB like this. And you know, and why is this is the vector, and the vector of VA is bigger than the vector of the vector of VA is bigger than the vector of VB, because I told you from the verse that VA is more than VB. So you are asked for the direction of VB with respect to A. So VB with respect to A will be equal to VB plus, sorry. So VB with respect to A. And from this to get it, so you know that VB will be equal to VA plus VB with respect to A. And to know and make sure that your equation is right, multiply the subscript A multiplied by BA. So you'll find that A goes with A, and you will finally have B is equal to B. That means that you construct this equation right. So to know VB with respect to A, so it's VB here with respect to A, it will be something like that. So how it will look like. So this is VB with respect to A. What if it's another direction, like something like this and something like that? And you will have, this is A and this is B. So this is VB with respect to A. So this is how it looks like. So let's see. Yeah, so this is how you construct your VB with respect to A. So what if you are asked of VA with respect to B? So here's VA and here's VB. So VA with respect to B, it will be something like that. So it's A if this is position of A and this is B. So this is VA with respect to B. So this is the direction. So it's completely different if you are asked of the velocity of car A with respect to B or car B with respect to A. Just make sure that you have the right direction. So from here, you can have that, or let's do this one. So this one will be equal, like here you will have VB, here's this one, is equal to VA plus VBA. Can you see the directions? You go from here to here. So if you want to go from like O to point B, and here's the VB, you can have VA in this direction, and then you come back with VB with respect to A. So just like some thought, I felt like I have to throw them, just like not to be confused. You don't have to be given numbers. You might like assume if I told you this is bigger than that, you might like want to construct a vector that is bigger than this vector, and then try to find the relative velocity based on your understanding. So you don't have to be given number, just to draw vectors and make one bigger than the other one so you can identify the relative velocity. Does anybody have any question here? Okay, see you guys tomorrow, and I hope that you guys are will prepare very well for your third quiz, and you will do great.
Thank you very much, Professor.
Thanks, guys. See you tomorrow.